This is on the boardwalk on Phillip Island, Victoria, Australia, one of my most favorite spots. I love to see the play, the unending play of water and earth, two great forces, one irresistible and persistent, and the other patient and unyielding. Isn't life like this with passion and tenacity? When I was a boy growing up in a small place called Dhruva in India, I never thought there could be a sight like this. But see the marvels of modern life with its airplanes and other forms of transport that we take for granted today as a part of our lives. A colleague of mine told me that back in 1980 or so, he took his four-wheel drive to a remote village somewhere in the Himalayas. The locals had never seen a motor vehicle before. Being very hospitable, they brought hay to feed the car. Well, it does not take too long for humans to adjust to any realities. So my hope is that within my lifetime, we may have ships going to and from the moon and the nearby planets as regularly as jet planes fly us to so many destinations every day. Now this gives us a clue as to what to do with our new motor, how to recover all the investments made for its development and production. I hope in my own lifetime. Let us put it on an aircraft and give joyrides to the rich people of the world, to the moon and beyond, into outer space. We will recover our investment fast enough. As an example, consider the Eiffel Tower. Impressive as it is also immensely profitable with people paying money to climb it. Now let us talk about how we can make such a ship in a very rough, absolutely preliminary manner, of course. 1,000,000 amperes. Let us start with that. A nice round figure, what? The main technical problem is to make a switch that will switch 1,000,000 amperes on and off with a minimum of resistive loss. But this is just the start. We will worry about the technical issues later. The value of current chosen will vary with the design. For now, we will try to see what kind of spaceship we can make if we can generate 1,000,000 amperes as the circuit current. For that, we need to see some design issues and design formulas. Now this is really presumptuous. It is a one-page design of a spaceship to the moon. Really. Well, what are we saying? Let's say, now just take a figure arbitrarily, 1,000,000 amperes of current. I know that is really a great deal of current because we normally use 3 or 4 amps and our switches, our fuses will blow at 15 amps. So 1,000,000 amps is a lot of current. But let's not forget that we have already generated in front of you 3,000 amperes, which is only 330 times more, and that too was average current. The peak could have been around 4,000 amps. So we have already done something on those lines, and it's a matter of scaling it up. So let's say we just take this as an arbitrary value, 1,000 amperes. Now how to generate that? We want to do it very safely, so we have got, say, a fuel cell bank of 30 volts. And we have got, say, a whole circuit internal resistance maximum of 30 microamperes. So if we divide these together, we get 1 milliamperes. Now for that, we'll just see that the rails have to be not just 1 inch by quarter inch, but 500 millimeters by 500 millimeters. And the length of a circuit will be 20 or 40 meters, depending. And from there, we will be finding out what is the resistance. Obviously, it will change as it progresses down the rails, the armature, because resistance will increase, but we'll talk about that later. But, well, that's how we get 1,000,000 amperes, at least. Just taking Ohm's law and nothing else. It's not quite correct, we'll see, but okay, but just for the sake of argument, let's say we have got 1,000,000 amperes. But what is the force? We just found out that the force varies as the square of the current. L is a constant, we'll talk about it later. It is actually the inductance per unit length. And for this particular configuration of rails and separated by 5 meters, we will find out that L is this value, 3.24 in 10 to the minus 6. But multiplied by I square, where I is 1 million, force is 3.24 into 10 to the power 6 newtons or 317 tons. But we won't get it all that time because you see the armature will have to come back. So let's take an efficiency of 50% with two sets of rails. We'll talk about it a bit later. So the average force will be 1.62 into 10 to the power 6 newtons, which is 158 tons of thrust. Now what does this really mean? It means that if you have got a ship here, let's say hypothetically I've got a long wire and there's a lossless pulley and you tie it to 158,000 kilos of mass. Then the gravity will pull it down and this will go up. And let's say this is happening indefinitely. So that is the kind of force which will be always acting when you have got this kind of thrust. Another way to look at it is like, let's see, it's like, this is just falling down a hole, only it's the other way around. Now suppose Mother Earth was right here and pulling it, right? And as it goes to hit Mother Earth also shifts by the same distance. So there is always a space, no matter how fast it is moving. So that is something like the way in which anti-gravity, which is a popular term, will work. Like if you have got an internal force which is more than the force of gravity, it will simply rise up. On the other hand, if you have a very heavy situation, then it can take advantage of the aerodynamic lift to go off like this, and then it will take off. And as it loses on the gravitational pull, it will go faster and faster. So what is the power that is required? Now we have got 30 volts and 1 million, so we need 30 megawatts of power. So if you have fuel cells, like we take hydrogen and oxygen and turn it to water, then this is the formula. 572 kilojoules are formed when you have 4 grams of hydrogen combining with 32 grams of oxygen. So 36 grams of fuel of hydrogen and oxygen will give 572 kilowatts. So if you have got a 30 megawatt power drive, which is made up of banks of fuel cells, we will need about 2 kilograms per second of fuel. And that gives us an idea about what will be the fuel requirement for a particular journey. So for traveling for 1 hour, we'll require about 7.2 tons. Well, that is the design of a spaceship at a very fundamental level. Now we had just talked about 1 million amperes, and that's a tremendous amount of current, and therefore the idea will be, well, it just can't be. But the point is that when you have got a huge cross section for the rails, like 500 millimeters by 500 millimeters or 0.25 square meters, then if it is copper, our calculations here show in my worksheet, which I have specially made for this, is that it will take 584 seconds for those rails to increase the temperature from 20 degrees to 70 degrees. And the 9 minutes is a long time, and we can have enough cooling involved to see to it that the temperature does not exceed very much beyond manageable limits. And so it is managing 1 million amperes is with our current level of technology is not impossible by any means at all. And another thing is that if you have got this big cross section, then the resistance per meter will be very less, of the order of 0.2 micro ohms. So you may remember we had budgeted for 30 micro amperes. Now if we have got, say, even 30 or 40 meters of rails and armature and all that, say 40 meters of rails, we still will have 8 micro ohms, which is below a budget of 30 micro ohms, because the remaining will be of 22 micro ohms will be for the internal impedance of the fuel cells and the contact resistances and all that. So together I think we can manage with 30 micro ohms. So what I'm trying to say is that having 1 million amperes is really not such a big deal as we might think, especially when I repeat that we have already generated 3000 amperes with my very modest means. Thank goodness for internet. We can do so many wonderful things. For instance, we can find out the inductance of a rectangular loop of rectangular wire by simply putting these values in this website. And then we get 3.24 microhenries, which is what we had taken. When we say that there is one side is 1 meter, so this is 3.2 microhenries per meter. And when, as we said, the spacing is 5 meters and the wire thickness is in rectangular 500 by 500. So this is how we get our value of 3.24 microhenries, which we have used in our calculations for making our spaceship to the moon and our nearby planets. Okay, back now. We have seen that with our railgun geometry and current flow of 1 million amperes, we get an electrical force of 3.24 million newtons, or over 317 tons when such a current is flowing. 1 Newton is about the force which a mass of about 98 grams will exert upon whatever is holding it at the surface of the earth. This force of 317 tons is equivalent to about 26 F-35 engines firing together. Now what about the mass or mass of the ship? The fuel cells weigh 30 tons, the fuel for 10 hours or 8 hours 40 tons, 120 passengers and crew 15 tons, and the airframe, rails, electronics, insulation, etc. another 60 tons, which is the average weight of a Boeing 737. Which means the ship weighs 145 tons when fully laden, add 17 tons of cargo to make it 162 tons. Once again, the force of 3.24 million newtons can only be applied to the ship as long as the armature is on the rails. This I have to emphasize. And that is, say, 25% of the time. When there are two sets of rails, like two cylinders on an engine, the efficiency will be 50%. Say maximum efficiency with 3 rails will be 75%, who knows. Let us take two sets of rails with 50% efficiency. Then we get 1.62 million newtons of thrust on the average. This is an extraordinary amount of thrust to give to a comparatively small plane carrying only 120 people. The thrust to weight ratio is more than 1. So its takeoff can be very rapid in a short space. Now let us see its acceleration in free space away from the Earth. From the formula, force is mass times acceleration. The acceleration on the average is 10 meters per second per second. In 1 hour of flight with power on, with no other forces to influence it, the ship with that kind of acceleration will reach a speed of 36,000 kilometers per hour. Let us talk of taking this ship to the moon and back. We fly for say 90 minutes with power on, and in that time we cover a distance of 145,800 kilometers, ignoring Earth's gravity. This is only a preliminary estimate after all. After that we shut the engines and coast at the speed of 54,000 kilometers per hour for about 1 hour and 42 minutes. Of course, with more motors and higher current motors, the size of the ship will be larger, or it could be faster. This example is only indicative. Then once again our engine is on, this time we decelerate or reduce our speed the same way as we had accelerated earlier, but this time our engine is pointing towards not the moon, but towards the Earth. We thus stop on the moon after another 90 minutes. So with this engine, we can reach the moon with a cargo and 120 people in 282 minutes. The round trip should take nearly that time. Looks pretty simple. We took 40 tons of fuel. We use about 2 kilograms of fuel per second. So we have used 29 tons of fuel. And which I must remind is made of hydrogen and oxygen, and both these elements are renewable. This conceptual ship could take us to Mars with the same fuel, but will take more time. Let us say it accelerates for 2.5 hours, decelerates for 2.5 hours, and then repeats for the return trip. In 2.5 hours, it will reach a speed of 90,000 kilometers per hour. Now, the average distance to Mars is around 220 million kilometers. The lowest distance is 54 million kilometers. Let us say we try to reach it when it is around 100 million kilometers away. We will reach Mars in 47 days. The round trip will take only 94 days. Suppose we have a nuclear reactor that can output 1 million amperes. and the ship has the same mass. I mean, that is really stretching it, but just suppose. Then the above trip can be done in 5 days. This will happen when the motor is always working, accelerating for half the distance and then decelerating for half the distance. Now let us get a bit crazy, just a little bit crazy. Say we have made a huge breakthrough, I don't know how or what. Instead of 1 million amperes for the same ship mass, the ship's engine with the nuclear plant generates 1 billion amperes. Now can we go to the nearest star? How long will that take? The nearest star is 40 trillion kilometers away. That is 4 followed by 13 zeros. However, when we generate 1 billion amperes, then our force increases by 1 million times and our acceleration increases by 1 million times with respect for our ship which will go to Mars. To reach half the distance between us and Alpha Centauri by continuously accelerating will take us in our new ship 18 hours. It can make the return trip to Earth in 72 hours. The top speed it will reach will be 2100 times the speed of light. I must say here that going beyond the speed of light is impossible according to all the modern physicists. We will consider this issue later. Also, it may seem impossible to generate 1 billion amperes today. However, 1 million amperes and more have been generated in the defense industry with their railguns. But now let us get even a bit more crazy. Say that our ship for the same mass generates 1 trillion amperes. Then the force and the acceleration will be 1 million times more than the ship which took us to Alpha Centauri. It will reach Alpha Centauri in 126 seconds. If it does not want to land there, it can reach it in 89 seconds. If we have a quadrillion ampere motor, it can reach Alpha Centauri in 90 milliseconds. This is very, very futuristic, of course. I haven't the faintest idea about how to make a quadrillion ampere motor. Plenty of new discoveries will have to be made. But yet, all of this comes from the analysis of our simple experiment that shows that the electromagnetic force acting upon a moving circuit element, causes no reactions to balance that force. Okay, this is all mind-boggling. Let us see now the theories involved, the historical development, the conflicts and controversies, the new ideas, and finally, how all this can perhaps take off.